Some of the most exciting reactions in organic chemistry are based on transition metals, which allow nucleophilic addition to an inactivated alkene. The first is the Heck reaction. The second, the Poisson-Kant reaction, is a special method of making 5-membered rings. Neither of these reactions is possible without the metal. There are 7 typical chemistry reactions with metal organics. Carbonylation is an important industrial process as carbon monoxide is a convenient 1-carbon feedstock and the resulting metal-acyl complexes can be converted into aldehydes, acids, and their derivatives. The oxo process is the hydroformylation of alkenes such as propane and uses 2 migratory insertions to make higher-value aldehydes. A catalytic cycle shows the various stages of alkene coordination, hydrometallation to produce an alkyl metal species, coordination of carbon monoxide followed by insertion, and finally reductive cleavage with hydrogen to produce the metal hydride intermediate, which is then ready for another cycle. Insertion reactions are reversible. The reverse process, decarbonylation, is also fast but can be arrested by maintaining a pressure of carbon monoxide above the reaction mixture. The reverse of hydrometallation involves the elimination of a hydride from the adjacent carbon of a metal alkyl to form an alkene complex. Other than beta hydride elimination, another important pathway by which palladium intermediates can lead to neutral organic fragments is reductive elimination. This forms the basis of the mechanism for cross-coupling reactions between an organometallic reagent and an organic halide or triflate. This is a reaction that seems very attractive for synthesis but, in the absence of a transition metal catalyst, the yields are very low. But in the presence of a transition metal, cupric compound for lithium and palladium compound for tin, coupling occurs stereospecifically and in good yield. Since the first reported use in the late 1970s, the Stille coupling has been widely used for the coupling of both aromatic and vinylic systems. The mechanism involves the oxidative addition of the vinyl or aromatic triflate or halide to give a palladium intermediate. This then undergoes a transmetallation reaction with the organose tannide, giving an organopalladium intermediate in which both components are sigma-bound. This complex then undergoes a reductive elimination step, releasing the product and thereby regenerating the palladium catalyst. Nicolao's synthesis of rapamycin uses the reaction twice in the macrocyclization step. This illustrates an important feature of palladium-catalyzed cross-couplings. The geometry of both double bonds involved in the coupling is preserved in the product. This is a very complex example and the molecule is complex. Since first being published in 1979, the Suzuki coupling of a boronic acid with a halide or triflate has developed into one of the most important cross-coupling reactions, totaling about a quarter of all current palladium-catalyzed cross-coupling reactions. The original version consisted of hydroboration of an alkyne with ketone boron, followed by palladium-catalyzed coupling of the resulting vinyl boronate with an aromatic iodide or bromide. The mechanism is very similar to that of the Stille coupling. Oxidative addition of the vinylic or aromatic halide to the palladium complex generates a palladium intermediate. This then undergoes a transmetallation with the alkenyl boronate, from which the product is expelled by reductive elimination, regenerating the palladium catalyst. The important difference is the transmetallation step, which explains the need for an additional base, usually sodium or potassium ethoxide or hydroxide, in the Suzuki coupling. The coupling of terminal alkynes with aryl or vinyl halides under palladium catalysis is known as the Sonogashira reaction. This catalytic process requires the use of a palladium complex, is performed in the presence of base, and generally uses copper iodide as a co-catalyst. One partner, the aryl or vinyl halide, is the same as in the Stille and Suzuki couplings, but the other has hydrogen instead of tin or boron as the metal to be exchanged for palladium. The mild conditions usually employed, frequently room temperature, mean that the reaction can be used with thermally sensitive substrates. Oxidative addition of the organic halide gives a palladium intermediate that undergoes transmetallation with the alkenyl copper. Reductive elimination with coupling of the two organic ligands gives the product and regenerates the palladium catalyst. Allylic compounds with good leaving groups, such as bromide and iodide, are excellent allylating agents, but they suffer from loss of regiochemistry due to competition between the direct SN2 reaction. In contrast, pi-allyl cation complexes of palladium allow both the stereochemistry and regiochemistry of nucleophilic displacement reactions to be controlled. The full catalytic cycle is shown with the intermediate pi-allyl complex in equilibrium between the neutral version, which has the leaving group coordinated to palladium, and the cationic pi-allyl, in which one of the phosphine ligands has displaced the anion. The presence of 5-membered rings has led to a variety of methods for their preparation. One of the most successful of these is the use of trimethylmethane cycloaddition, catalyzed by palladium complexes. The trimethylmethane unit in these reactions is derived from 2-trimethylsilyl-methyl-2-propan-1-L acetate, which is at the same time an allylsilane and an allylic acetate. This makes it a weak nucleophile and an electrophile in the presence of palladium. Formation of the palladium pi-allyl complex is followed by removal of the trimethylsilyl group by nucleophilic attack of the resulting acetate ion, thus producing a zwitterionic palladium complex that can undergo cycloaddition reactions. The normal course of the reaction is to react with an alkene with electron-withdrawing substituents present, which make the substrate prone to Michael-type conjugate addition. The resulting cyclization product is an exomethylene group. Cyclopentanes illustrate this overall cycloaddition. Alpha chemistry has created a tangible competitive advantage for customers with high quality as well as optimal prices. Most of our products can be supplied ranging from milligrams to kilograms scale and arrived with technology documents.